Hello, in this lecture we will learn how to add matrices, multiply a matrix by a scalar, and we will also look at linear combinations and the definition of the transpose of a matrix. So let's start with the sum of matrices. Here's the definition. We have two matrices, which we are adding. Now the matrices must have the same dimension. Notice that both matrices here have dimension m by n. And the sum is performed component-wise. So here we have our first matrix A, our second matrix B. We take each component from A and B and we add them up to get the sum. So that's pretty easy. The sum is commutative. So A plus B equals B plus A. Here's an easy example. So we have our matrix A here, our matrix B. And when we add components, again, we add corresponding components. So 1 plus 4, which is 5. 2 plus 3, which is also 5. And 3 plus 2, 5. And 4 plus 1, 5. And of course, if we do B plus A, we get exactly the same thing, OK? All right, now let's look at the scalar, how to compute a scalar multiple of a matrix. So alpha is a scalar here, which simply means a number. And the multiplication is done, again, component-wise. So we take each entry of the matrix A and we multiply by alpha. So alpha A11, alpha A1n, and so on. So here's an easy example. The matrix A has all entries equal to 1. We multiply by alpha equals 5. And of course, we get a matrix with entries all equal to 5. The multiplication by a scalar is consistent with the sum of matrices, meaning what? Well, if this is our A and we multiply by 2, we get the same result as performing A plus A. And of course, that's exactly how it should be. All right, now let's look at the definition, which is actually very important. If you're given a set of vectors, we have n vectors here, v1, v2, vn, and x1, x2, xn are scalars, so just numbers, then x1 times v1 plus x2 times v2 plus xn times vn is called a linear combination of the vectors. Of course, the vectors v1, v2, vn. Note that it is possible for scalars to be negative or equal to 0. So this x1, x2, xn could be all negative, could be equal to 0, or some of them could be equal to 0. Linear combinations of matrices can be obtained in a similar way. So let's look at a quick example. OK, so here we have two vectors. So we can call them v1 and v2 to be consistent with our definition. OK. And we put a scalar in front of v1. In this case, it's 1. So that would be our x1. And then we put a scalar in front of v2, which we can look at as our x2, and we add. So when multiplying by 1, of course, doesn't do anything. We get the same vector v1. When we multiply by 2, the vector v2, we get the vector with components 2, 2. Then we add them up and we get 4, 1. So this 4, 1 is a linear combination of v1 and v2. Of course, we can pick any value for x1 and x2, and we can obtain infinitely many linear combinations.
So the addition of any two vectors is also a linear combination?
Absolutely. Very good question. If we do v1 plus v2, right, which in this case would be 2 minus 1 plus 1, 1, this is also a linear combination. The coefficients, what would x1 be in this case?
1.
Exactly. It would be just 1. And the same for x2. So there are no restrictions of x1, x2, xn. They can be equal to each other, in particular, both equal to 1. And of course, so here we get the vector 3, 0. Again, this is a linear combination of v1 and v2. Now let's see at a graphical interpretation of linear combinations. So we get also used to sketching vectors. All right, so we have the vector 2, negative 1 here, the graph of the vector 2, negative 1. How do we get it? Well, we move 2 units in the x direction, or x1 direction, and 1 unit, 1 and -1 in the x2 direction, right? So then we graph the vector 1, 1. So again, 1 in the x and 1 in the y. Now let's look at the linear combination here. It says I want to multiply the vector 2, -1 by 1, which means, well, I'm getting exactly the same vector, right? It doesn't change. But then we're going to multiply the vector 1, 1 by 2. What is that going to do to the vector 1, 1?
It's going to make it twice as long.
Exactly. It's going to make it twice as long. So this is the vector 2 times 1, 1. Then we need to add them. And in order to add them, we are going to use the parallelogram rule for the addition of vectors. Now, how does that work? We build a parallelogram from these two vectors. So this side is parallel to this one, and these two sides are also parallel. The sum is going to be the diagonal of this parallelogram, which of course is 4, 1 as it should be. We had already computed the linear combination. So 4 in the x direction and 1 in the y direction. Okay? All right, now let's look at the transpose of a matrix. That's an important definition. We're going to use it throughout the course. The transpose of an m by n matrix A is an n by m matrix. Notice here that the dimensions are switched. It's denoted by A with a subscript T, so A transpose, whose rows columns are the columns rows of A. Let's look at an example, a few examples. Here's an easy one. This matrix is, what's the dimension? It's actually a vector, it's a row vector, right? What's the dimension?
1 by 2.
1 by 2. And so if we do the transpose, we should get a 2 by 1, which is exactly what we do. Really, all we're doing here is changing this row vector into a column vector. And if we start with a column vector of dimension 2 by 1, we take the transpose, of course, we end up with a row vector. Now let's actually look at a matrix. This is a 2 by 2 matrix, so the transpose will also be 2 by 2. And what's the first row of the transpose?
2, -1.
2, -1, absolutely, because it's just the first column of our matrix. And the second row of the transpose will be
1, 1.
1, 1, which is the second column. Okay, let's look at property of the transpose, which is actually pretty intuitive. If the transpose of the transpose is the matrix A itself, right? If we switch again rows and columns here, we get back our original matrix. And an important definition related to the transpose, a square matrix, so a matrix for which m equals n, is called symmetric if the transpose of A equals the matrix A itself. And here's an example. Now you can see that the transpose equals the matrix A because, well, if you look at row 1, it's the same as column 1. So switching them is not going to do anything. Row 2 is the same as column 2, and so on. But we can also think of a symmetric matrix in terms of symmetry, in the sense that entries are symmetric across the diagonal. For example, these two entries are the same and equal to 2. These two entries are the same, and these two entries are the same, right? Okay, any questions? Thank you.